Hi guys, we are going to continue our talk on vectors today and looking at another operation, but before we do I would like you to try this warm up. So hit pause, try the warm up, and we'll come back and look at it. Okay, so we are going to find the region, the area of the region R, which is that shaded region up here. And to do that, we are going to need to figure out our bounds of integration. It might help. I like to see my table of values. I kind of like to see how my graph is going. So I will typically look just to make sure I have a visual of what's happening in my graph. So theta and r. We'll start with theta equals 0. And if I plug theta equals 0 in, I get 2 minus 4 times the sine of 0. So I just get 2, which makes sense. That's our point right there. And if I continue around and I go to pi over 2, since that's my domain, I know this is going to be this point right here. So pi over 2 is going to give me negative 2. Okay, so it bounces back, back down here to 2. So then I need to figure out, I know my lowest bound of integration is going to be 0. And then I need to figure out what is going to give me this point. So I am going to set 0 equal to 2 minus 4 sine of theta. And I'm going to solve. So we get 1/2 equals the sine of theta. And then the theta equals pi over 6. So now to set up my integral, I have 1/2 from 0 to pi over 6 of 2 minus 4 sine theta squared d theta. And I can type that into my calculator. In doing so, I get approximately 0.3377. All right, let's move on to the equation of the line tangent to the graph at theta equals 0. And you'll notice I did not give you enough room for this. At least I didn't give myself enough room. So I'm going to come over here and we need to find the derivative. But the problem is I need to parameterize this function first. So let's see where I can write this. I'm going to do, we'll write the first one up here in this picture. So I need to use the fact that x equals r cosine of theta. And I'm going to make a substitution in with the r that I know. So x equals 2 minus 4 sine theta cos theta. And then I need to take the derivative of this. So the derivative of x with respect to theta is going to be, derivative of the first is negative 4 sine, oops, no it's not. Let's just erase that. See if I can get that off. There we go. Okay, so we get negative 4 cosine theta, derivative of the first times the second, plus the derivative of the second, well, the derivative of cosine is negative sine, times the first, 2 minus 4 sine theta. Okay, and I could simplify this, but I'm going to evaluate it when theta equals 0. I don't have a way to show that right there, so we'll do dx d theta evaluated at 0 would give me, so this would give me negative 4 times 1, and this would give me 0 times everything. So my value would be negative 4. Okay, so we're going to do the same thing for the y. So y equals r sine theta, and that means y equals 2 minus 4 sine theta. And then when I take the derivative of y with respect to x, we get derivative of the first is negative 4 cosine of theta times the sine of theta, plus the derivative of the second, which is cosine of theta, times the first, 2 minus 4 sine theta. All of this evaluated at 0. And if I substitute 0 in, let's see, we get negative 4 times 0, that goes away. Then we get 1 times 2, so dy dx equals 2. So what I know now is I know that the slope that I'm looking for is dy d theta over dx d theta. So my slope is going to be 2 over -4, or -1/2. Now, I need the point. So to find my point, I'm going to use the x equals and the y equals that I started with, and I'm going to substitute in theta equals 0. And doing that, theta equals 0 for x, we get 2 times 1, so I get 2 for the x value. And for y, I get theta equals 0, I get, let's see, 2 times 0, so that's 0. So my point is 2, 0, my slope's -1/2. So we do all that work to get the equation of the line. Oops, -1/2, x minus 2. Okay, how'd you do? All right, let's move on to our vectors. Okay, so today we're going to talk about a third vector operation. So far we've looked at vector addition and multiplication by a scalar, but today we're going to add a third operation to vectors, which is dot product. And the dot product of two vectors, lost my pencil, my dot product of two vectors, if I have vector u, which the components are u sub 1 and u sub 2, and the vector v sub 1 and v sub 2, to find the dot product, and we notate it like this, we'd say vector u dot vector v. It literally looks like a multiplication symbol, maybe a little bit bigger, but not by much. So u dot v equals u1 times v1 plus u2 times v2. Now in 3 dimensions, it's really not much different. When we do the dot product of u dot, oops, that was supposed to be a v, u dot v, we take and multiply the components. So we have u1 v1 plus u2 v2 plus u3 v3. And that's the dot product. Now, the key to this is you'll notice I'm multiplying a component or two components together and then adding them to other two components multiplied together. So we know that the dot product is a scalar. It's a scalar quantity. It is not a vector. It does just give us a scalar quantity. Now, if we look at the geometric interpretation of this, if I look at u dot v, it can be defined geometrically in terms of the angle theta that's between u and v. So if I have two vectors in space, theta is the angle that is between them, and the geometric interpretation of the dot product is that u dot v, didn't realize I switched colors, oh well, equals, sorry, I thought I stopped recording, equals the magnitude of u times the magnitude of v times the cosine of theta. Okay, so let's see. Earlier we said that the dot product, u dot v, was equal to u1 v1 plus u2 v2. And then, just before this, the geometric interpretation, we said that u dot v was equal to the magnitude of u and the magnitude of v cosine theta. So, are these really equal? Is that true? Can I prove that those are equal? Well, we're going to do that. So what we're going to do is we're going to use the law of cosines, okay? And the first thing that we want to do with this is I am going to find the side lengths as magnitudes. Okay, so here's what that's going to look like. Let's call this vector u, and so let's give it the components u1 v, let's not do u1 v1, Let's do u1, u2 as my two components. Okay, what that means is that the magnitude of u is equal to the square root of u1 squared plus u2 squared. Do you feel good about that? And if I do v, I'm going to call this v1 and v2. Those are my components. And therefore, the magnitude of v would be v1 squared plus v2 squared. Okay, so since this green vector here represents subtraction of vectors, remember if it's addition of vectors, we would take, like for example, u and add it to v, we would put it in the same direction just from the tail end of v, the ending point of v. So for this one, to find u minus v, do you agree that the components of this would be u1 minus v1 and then u2 minus v2? Those would be the components. And so if I look at the magnitude of u minus v, the magnitude of vector u minus vector v, this would be the square root of u1 v1 plus u2, that was supposed to be a minus, u1 minus v1 plus u2 minus v2 squared. Do you agree with that? Okay, so the hint that was given was to use the law of sines. Okay, so it says use the law of sines, but that requires, it says cosines. That requires you to know the law of cosines. So do you remember that the law of cosines says if we have c squared, it's equal to a squared plus b squared minus 2 times a times b times the cosine of c. Okay, well, let's fill this information in. We are going to because we're trying to find this angle theta here, we're going to let u minus v be the c squared. So my c squared is going to be the side vector u minus vector v. Okay, so what that's going to look like is in place of c squared, I'm going to put what the magnitude of u minus v squared. That's c squared. And then I'm going to set that equal to a, which can be either u or v, so let's just let it be u. I'm going to let that be the magnitude of u squared, because the magnitude is the length, plus b squared, which b squared would be the other side, so we're going to call that vector v, the magnitude of vector v squared. And then we're going to do minus 2 times a, well, a we let be vector u, so that would be the magnitude of u, times b, which is the magnitude of v, times the cosine of c. In this case, our c is our theta. Do you agree with that so far? Okay, so what I'm going to do now is in place of the magnitudes, I'm going to plot what the magnitudes equal in place of the magnitudes. So let's start with the magnitude of u minus vector v. That would be the square root of, let's see if I can write this small enough, u1 minus v1 squared plus u2 minus v2 squared squared. That's going to equal the magnitude of u squared. So the magnitude of u squared is the square root of u1 squared plus u2 squared plus vector v, the magnitude of vector v, we've got the square root of v1 squared plus v2 squared minus, now I'm actually going to leave these magnitudes as they are, and I'll show you why in just a minute, because we're trying to show that u1 v1 plus u2 v2 is equivalent to this. So I'm just going to leave the magnitudes in their place. Okay, so simplifying, we get something that's a bit of a mess. So simplifying this first one, I get u1 minus v1 squared plus u2 minus v2 squared equals u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2 times the magnitude of u, magnitude of v, cosine of theta. Okay, now doing some algebra, we get u1 squared minus 2u1v1 plus v1 squared. Foiling the next one, we get plus u2 squared minus 2u2v2 plus v2 squared equals u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2 times the magnitude of u, magnitude of v, cosine of theta. Okay, so now we get to do some fun algebra. We know that with this, I have a u1 squared, goes away with the u1 squared, v1 squared, v1 squared, u2 squared, u2 squared, v2 squared, v2 squared, and then I'm left with this negative 2u1, oops, that was a 1, subscript, v1 minus 2u2v2 equals negative 2 magnitude of u, magnitude of v, cosine theta. Bet you can see where this is going now. And if I divide everything by negative 2, I get u1 v1 plus u2 v2 equals the magnitude of u, magnitude of v, cosine theta. Isn't that pretty cool how that works? So we were able to prove that the dot product is both u1 v1 plus u2 v2 as well as the magnitude of u times the magnitude of v, cosine theta. All right, well, let's use this now. All right, so we know that, let's change it to A and B. So this says find, oops, let's put this on a pencil. Sorry to make you a little bit dizzy. We know that we're trying to find A dot B. And if I do A dot B, we know that it's equivalent to A1 B1 plus A2 B2, or the magnitude of A times the magnitude of B, cosine of theta. Okay, so we get to determine which part of this we're going to use. Okay, so we can use either piece of this, and I'm going to choose which one to use based on what's given to me. So for example, on this first one, it says that the magnitude of A is 3, magnitude of B is 3, right? 5. Right there, I know I'm going to use this portion of the dot product. So it says that the magnitude of A times the magnitude of B times the cosine of theta. I have all that information. So if I want to find A dot B for this example, I'm going to do the magnitude of A, which is 3, times the magnitude of B, which is 5, times the cosine of pi over 4. And if I do that, cosine of pi over 4 is root 2 over 2. So we get, I don't know what happened to the pressure of my pencil, it seems to be off. We get A dot B is equal to 15 root 2 over 2. Okay, but you'll notice in this next example, I'm only given the component form of the vectors, and so therefore it's not going to do me any good to find, I don't have an angle, so I can't use this piece. So I'm going to do the component form this time. So when I set this up, A dot B, I know it's going to be equal to 2 times 0 plus 3 times 1 plus negative 1 times negative 2. So we get 0 plus 3 plus 2. So we get A dot B is 5. And that makes sense because remember the dot product is a scalar. All right, for this last one, I am going to put each of these in their component form. So I'm going to do negative 4, 1, -2. And then for b, I'm going to put 3, -1, 1. And then we're going to do it the exact same way we did number 2. So try it and see what you come up with. Hopefully when you do a dot b, you get -4 times 3 plus 1 times -1 plus -2 times 1 to get -15. Okay, let's move on. So we can use the dot product to find the angle between two vectors. Well, that should make sense because we've talked about how the u dot v, vector u dot v, is equal to the magnitude of u times the magnitude of v cosine theta. So doesn't it make sense we could use that to be able to find the angle between two vectors? In fact, we may even want to rewrite this as the cosine of theta equals the dot product between u and v divided by the magnitude of u, magnitude of v. Okay, so let's try an example. Let's try this first example. It says, let's find the angle between u and v. So the first thing that we need to do is we need to find the magnitude of u and the magnitude of v. And if I find the magnitude of u, I get the square root of 1 squared plus 0 squared plus -2 squared to get the square root of 5. And the same thing with the magnitude of v. So 2 squared plus 1 squared plus -1 squared equals the square root of 6. All right, but then I need to do the dot product between u and v. So u dot v to get, we're doing u dot v. So 1 times 2 plus 0 times 1 plus -2 times -1. And so my dot product is 4. So using this formula right here, what I can set up is I can say that the cosine of theta in my problem is going to be equal to 4 over the square root of 30, or the square root of 5 times the square root of 6. So we get cosine of theta equals 4 over root 30. And then I can take the cosine inverse of this. So theta equals the cosine inverse of 4 over root 30. So if you would like to try the next two, although they're very similar, you can go ahead and do that. I'm just going to give you the answers right now, and you can check your work against the answers. So on u and w, the angle that is between them is theta equals pi over 2. And between v and w, the angle that's between them comes from the cosine inverse of 6 over root 84. Hopefully you did okay on those two. I just would like to keep moving since we've got a lot of notes. So if you'd like to go back and try those, please feel free to do so. Okay, the beauty about that is the angles between two vectors is when we do this, we can see some interesting characteristics about the angles just based off of the dot products. So using the formula of a dot b over the magnitude of a times the magnitude of b equals the cosine of theta, I know that some characteristics of theta based on the dot product. If a dot b is greater than 0, my theta is going to be acute. But if my a dot b is equal to 0, then theta is going to be pi over 2, and pi over 2 is equivalent to 90 degrees. So theta is going to be the 90 degrees. A and b are going to be perpendicular to one another. And if a dot b is less than 0, then theta is going to be obtuse. In dealing with vectors, we can determine whether they are orthogonal, parallel, or skew. Now, first of all, let's define orthogonal because we probably haven't used that word too many times. Means that the vectors form a right angle or form 90 degrees. They're perpendicular. So what did we just talk about? A way to make vectors perpendicular would be to make that their dot product is 0. If their dot product is 0, then the vectors are considered orthogonal, or they are perpendicular to each other. Now, if vectors are parallel, so if I have any vector and I want it to be parallel to another one, it's going to be multiplied by some scalar. So this is some scalar that we're going to multiply by, and that will make the vectors parallel. So we're going to look to see if the following vectors are orthogonal, parallel, or neither. So basically parallel, perpendicular, neither. Okay, so the first thing we want to do is find the dot product, because the dot product will tell us whether they are orthogonal. So we're going to start with that. On this first one, if I do u dot v, I get negative 5 times 3 plus 4 times 4 plus negative 2 times negative 1. So we get negative 15 plus 16 plus 3. So that'd be 2. Goodness. So we get that u dot v is equal to 3. Okay. So we know that the dot product not being 0 means they're not orthogonal. So now we need to determine if they're parallel. Is there some way that I can multiply u by something to get v? Is there some way that I can look at negative 5 divided by 3, so u divided by v, and make it equal 4 divided by 4, or make it equal negative 2 divided by negative 1? Is there any way that those are true? And if the answer is no, it means that they are not multiplied or related by a scalar. So this would be an example of neither. Okay, try the next two. Okay, so for the first one, if we look at the component form, we have 9, negative 6, 3. And then for v, that's u. For v, we have negative 6, 4, negative 2. So if the first thing that we do is look at them and determine their dot product, if we do u dot v, I get 9 times negative 6, so negative 54. Then I get negative 6 times 4, so I get a negative 24. And the next one's negative 6. These do not equal 0, so therefore it's not orthogonal. So now let's look at the ratio of the vectors. If I compare 9 to negative 6, and I compare negative 6 to 4, and I compare 3 to negative 2, is there any relation between those three ratios? Well, they're equivalent. So since they're equivalent, I know that vector v is really just a scalar multiplied by its v to give me u. So therefore, these two vectors are parallel. Okay, let's look at this last one. I may scroll up just a tiny bit. So let's look at this last one. First, let's test for being orthogonal. So if I do, oops, again, didn't get my pencil. If I do u dot v, we get c times c plus c times 0 plus c times negative c. So we get c squared minus c squared, which is 0. I don't even have to deal with parallel because the dot product is 0. These are orthogonal, meaning those two vectors are perpendicular to one another. Okay, I am going to scroll again. We are now going to look at some of the properties of dot products. Okay, so let's look at some of the properties of dot products. Here's what it says. It says that if we have u dot v, it's equivalent to v dot u. We could prove this pretty quickly. If we do u dot v, we would have u1 v1 plus u2 v2. If we do v dot u, we would do v1 u1 plus v2 u2. Are those equivalent? Yeah, sure. They're the same thing. Multiplication's commutative. Okay, so if we take and multiply, sorry, we don't multiply. If we take and add the two vectors together, v and w, and then take the dot product of those, they will be equivalent to u dot v plus u dot w. Okay, here's what that looks like. So if I do, let's give these component forms, let's call them u1, u2, dot, well, if I add two vectors, we would have v1 plus w1, comma, v2 plus w2. Do you agree with that? And if I do the dot product of those two, I get the first components multiplied, so u1, v1 plus w1, there's u1, plus u2 times v2 plus w2. And distributing that, we get u1 v1 plus u1 w1 plus u2 v2 plus u2 w2. Okay, u dot v, let's do that in a different color. If we do u dot v would be this term with this term. And if we do u dot w, it would be this term with this term. So the dot product has that property as well. The third property that it has is pretty self-explanatory, that if I take a scalar c and multiply it by the dot product of u dot v, it would be equivalent to multiplying the scalar by u, then taking the dot product, or multiplying u dot the scalar times v. Okay, a couple others. The 0 vector dot product with u vector. So 0 vector is 0, 0. The u vector is u1, u2. And if I do the dot product of that, I'm doing 0 times u1 plus 0 times u2. So we get 0. Okay, last one. If we have v dot v, so let's give these names, v1, v2, dot product with v1, v2, should equal the magnitude of v, and we know the magnitude of v, magnitude of v squared, the magnitude of v is v1 squared plus v2 squared, but I'm squaring it. Okay, doing the dot product on the left-hand side, we get v1 squared plus v2 squared. And simplifying the right-hand side, I get v1 squared plus v2 squared. Okay, so those are our properties of dot products. All right, one important use of dot products is in projections. Okay, so the first type of projection we're going to talk about is a scalar projection. And a scalar projection of u onto v is the length of the segment. Well, let's look at it actually. Let's draw a picture. So if we draw a picture that looks like this, let's do u. Let's draw a vector. We'll call this u. Onto v. We'll call this v, vector v. Okay. If we drop this down here, this length right here, we'll highlight it in green, is the same length as u, vector u. So we call this the vector projection, the scalar projection of u onto v. Okay, picture it like a shadow. what a shadow might look like. Now, obviously, a shadow could be extended based on where the sun is at, but picture a sun perpendicular. What does the shadow look like? And that's what that looks like, the idea of that picture. Okay. Now, when we write this, when we talk about scalar projection, it's basically the component of u in the direction of v. Keep in mind, component is where it comes from. So when we write the formula for this, we say the components of u in the direction of v. So v becomes like a subscript, okay? And the way we do that is we're looking at the magnitude of u, the length of u, and so we get the magnitude of u times the cosine of theta, okay? So this component of u in the direction of v is this distance right here. Component of u in the direction of v. So it's that distance. Okay, so if we think about finding that distance, and we know this angle is theta, we would say that theta is equal to, or the cosine of theta equals, let's do it this way. Yeah, let's just say, if we said this, we would say the cosine of theta equals the component of u in the direction of v over the magnitude of u. Okay, so you can see where this formula comes from, is just from the formula of cosine. Now, what do we know? We know from before that the dot product of u dot v is equal to the magnitude of u times the magnitude of v cosine theta. Keep that in mind, because I can rewrite this, change it so that I only have the cosine of theta times the magnitude of u by doing the cosine of theta magnitude of u equals the dot product of u dot v over the magnitude of v. So this is equivalent to the dot product, that's why this is important, over the magnitude of v. Okay, so that's the scalar projection. Now, when we talk about the vector projection of u onto v, of the difference between the scalar projection and the vector projection is that the vector has a length and goes in the same direction as v. Okay, so mathematically, the scalar projection of b onto a, where we have this formula, is part of the vector projection. It's merely the unit vector of the component in the direction of v. So let's look at what that looks like pictorially. We have this picture up above that we can see, okay? And if we want to label this now as a vector, so a vector projection, not just the length, we'll call it w, then the vector projection here, w, is equal to the component of u in the direction of v multiplied by vector v over the magnitude of v, because we need to multiply by the unit vector. Okay, so here's what this looks like. The notation for this is a little bit different. We call this the projection of u onto v. It's opposite of what it looks like there. Projection of u onto v, and it's equivalent to the component in the direction, the component of u, in the direction of v, too many things to write. My mouth should stop talking while I'm writing, multiplied by the unit vector of v. So it's in that same direction, but it's a unit vector. But what we know is that the component of u, this in the direction of v, we know that this piece is equivalent to what we said up above. Okay, so I'm going to rewrite this to say that the projection of u onto v is equal to u dot v, magnitude of v, times the unit vector of v. Okay? All right. That's a lot to take in. So let's look at what we use this for even, and how it applies to the some of the problems that we have coming up. Okay, here we go. We're going to find both a scalar and a vector projection of B onto A. Okay, so of B onto A. So what this looks like, let's start with the scalar. Okay. If we look at a picture of this, this would look something like this. I have a vector A, and then I have a vector B, whatever that looks like, wherever they are. And this angle here would be my theta. And so I'm making projection of B onto A. Okay, so the scalar form says we're going to take the component of vector B onto A. And we remember we do that by doing the dot product of A dot B over the magnitude of A. Okay, so using the values that we have, I'm going to go through and substitute these in, and we get A dot B, we would get -2 plus 3 plus 2 over the magnitude of A, I would get 4 plus 9 plus 1. So we get 3 over the square root of 14. So my scalar projection would be a value of 3 over root 14. Okay, now my vector projection. So my vector projection is basically saying send your scalar projection, send that in the direction of A. So what I need first is I need to find the unit vector. So I need to find a unit vector for A. Okay, so to do that, I'm going to take vector A and divide it by the magnitude of A. Well, we've already done the magnitude of A, so I know my unit vector is, in this case, would be -2 over root 14, and 3 over root 14, and 1 over root 14. So then, therefore, the projection of B onto A is equal to the component, or the scalar projection, of 3 over root 14 multiplied by this vector that we just found, the unit vector, which, simplifying, it's kind of nice, those are all root 14. So simplifying this, we get 3 over 14. Okay, where the projections really come into play is actually some pretty strong physics examples. So let's look at an example dealing with work. Okay, so as you can see, work, one of the uses of projections occurs in physics, which is calculating work. So the work done by a constant force F in moving an object a distance d is W equals F times D. So this only works when the force is directed along the line of motion of the object. Okay? But suppose, however, that the constant force is a vector F pointing in some other direction. Okay? So we have this vector F that's pointing in a different direction than where the object is being moved. So the work done normally applies only when the force is directed along the line of motion of the object. So if you're pulling from right here and you're moving the object along this line, that's where the formula W equals force times distance applies. Now, if we don't have that, if our force is pulling up here, but we're trying to move it in this direction, still in that same direction, if the force moves the object from P to Q, okay, so the force is moving in this direction, then the displacement vector D, which is right here, is equal to PQ, and the work done by the force. That is where we use the component of U in the direction of V. So in our case, we're going to use the component of F in the direction of D. So here's what that looks like. Let's put it in a pencil. We would get the magnitude of F cosine theta, which is equal to the component of F in the direction of D, which is equal to the dot product of F and D divided by the magnitude of D. Okay, so really what we're saying is the magnitude of F in the direction of D. Okay, that's what this is saying. Okay, so what we know is that this implies that work is the magnitude of D multiplied by the force in the direction of D, which means that work is the magnitude of D multiplied by one of those options. So the magnitude of force times the cosine of theta, which is the same as the component of force in the direction of D, which is equal to, oops, sorry, that was supposed to be an F dot D over the magnitude of D. Okay, so all of those are equivalent. So essentially what we have is that work is equal to the vector D dot vector F. Okay, let's look at an example where we can put this into practice. So I put this formulas up here. So it says a wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. Okay, so you can see the actual wagon picture, but here is genuinely what this looks like if we look at our picture. And using the formula that we just talked about, work is equal to the force vector dot D vector. Okay, and so that would be equivalent to the magnitude of F times the magnitude of D, be equal, cosine of theta. And so we know that information because it says that the wag is pulled a distance of 100 meters along a horizontal path. So we know that D is 100 by a constant force of 70 newtons. So that force would be, the magnitude of that would be 70. And that the angle is 35. So I can say that the work here is 70 times 100 times the cosine of 35. So we get 7,000 cosine of 35, which means the work here was 5,734 Newton meters. Yeah, those are the units. So that's an example of where we could use dot product or the ideas behind dot product to help us with physics even. So, all right, so now your assignment is on 12.2, dot product on WebAssign, and we will see you soon.